Much. I will have a series of presentations on the topic which I mentioned. One is about assessment of exposures to people after nuclear accidents, and the other is dealing with the assessment of exposures in the post-closure period of nuclear waste disposal. I will start with the first, which deals with a assessment of exposures to people from nuclear accidents. First of all, I will give an introduction on a very general issue, which is radioactivity and radiation exposure from natural sources. As you all know, radioactivity is a phenomenon, is a natural phenomenon, and it means it is a disintegration of atomic nuclei and the simultaneous emission of energetic radiation. I think you all know that elements comprise of atomic nuclei, and an element is defined by its number of protons. However, the number of neutrons varies, and therefore any element has different isotopes. Non-stable isotopes of an element are called radioisotopes. And radioactive atoms in general are called radionuclides. In total, we know now about 118 elements, and only 80 of these 118 elements have stable isotopes. In total, there are about more than 1,000 radionuclides. Where do these nuclides all come from? There are three main groups. The first group is the primordial radionuclides. They exist since the creation of the Earth. Cosmogenic radionuclides are generated due to the interaction of cosmic radiation with atoms at very high altitudes in the atmosphere. And man-made radionuclides, they exist now since about 70 years or 80 years, and they are generated in nuclear installations as nuclear power plants or research reactors or accelerators. The decay of any radionuclide is specific. It is specified by the radiation type, whether it emits alpha radiation, beta radiation, or gamma radiation, and also by the energy of the radiation which is emitted. This energy is measured in units of electron volts. Usually, the emission of alpha and beta radiations is accompanied by the emission of gamma radiation. The alpha radiation, these are very or relatively heavy particles. They consist of a helium nucleus, there are 2 neutrons and 2 protons. The range in air is very short, it's only a few centimeters, and the range in water is about a millimeter. Beta radiation consists of electrons, and they are smaller and lighter, so the range is a bit longer. And this is about some 10 centimeters to some meters in air, depending on the energy. The range in water is some millimeters. Gamma radiation, this is electromagnetic radiation. The range in air depending on the energy, can be up to some 100 meters, and the range of water is about 10 centimeters. X-rays is our gamma radiation with an energy in the range of 50 to 100 kilo electron volts, and the characteristics are similar. Each radionuclide is characterized by its physical half-life. And the half-life is the time required until the activity decreases to 50%. Half-lives of radionuclides vary widely from very small fractions of a second to billions of years. The activity of a radionuclide is measured in becquerel. 1 becquerel means 1 decay per second. However, the activity is an important unit, an important quantity. However, by the end of the day, we are interested in the energy which is deposited in tissue, human tissue, organs, bones, whatever. And the quantity for this unit, for the dose, is the millisievert. So we have the energy emission, the transport, and then the energy absorption. And the energy absorption is a measure for the dose, which is quantified in units, in millisievert. Why are we interested in doses? Why do we want to know how much energy is absorbed by tissues? The alpha, beta, and gamma radiation is also called ionizing radiation. This is because, due to the high energy, this radiation is able to form free radicals. These free radicals may interact with cells, and they may also damage the cell nucleus or damage the DNA. And possible effects are, for example, cell killing, or the malignant degeneration. This means the formation of a cancer cell. And it may also come up with mutations. And because of these adverse effects of radiation, we need also radiation protection. Let me come back to the range of the gamma radiation and of X-rays. This is important for shielding radiation. And the range depends first on the energy of the gamma radiation. This is a range here from 20 kilo electron volt to 5 mega electron volt, and for different materials, for air, for water, for concrete, and for lead. And as you see, the higher the energy, the longer is the range in a specific material. On the other side, the range of gamma radiation decreases with the density of the material. The more dense the material is, the lower is the range. This has been marked in red. This is the range between 500 kilo electron volt and 1 mega electron volt. And in between we have the relevant gamma energy for cesium-137, which is 662 kilo electron volt. And what you see for this gamma radiation emitted by cesium-137, the range in air is about between 70 and 80 meters. It can very well shield it or attenuate it by concrete. So this means if you have a radiation source outside in the environment and you stay inside, the walls or the structures of the building provide a shielding and an attenuation effect. By the way, the range of X-rays, the energy of X-rays is between 50 kilo electron volt and 100 kilo electron volt. And you may have already experienced that during an X-ray examination, those parts of the body which are not subject to examination will be protected by a lead tissue, by a lead shield. And you see already a lead with a thickness of less than a millimeter will decrease the radiation from X-rays already by 50%. Let's come to the natural radionuclides in the body. Naturally in the body. In the body we have about, each of us, about 10,000 becquerels of activity. 4,000 of this is due to potassium-40, which is a primordial radionuclide. This means it exists already since the creation of the Earth. So half-life is 1.3 billion years. I think the other main contributors regarding the activity is carbon-14, which a half-life of more than 5,000 years, which is generated in upper layers of the atmosphere, and tritium. This is radioactive hydrogen. So potassium-40 is an essential element for all life on Earth, for plants and for animals. So any food we eat, or nearly any food, contains some potassium-40. A typical concentration of potassium-40 for milk is about 50 becquerel per kilogram, and for meat about 50 to 100 becquerel per kilogram. Vegetables varies more widely depending on the use of fertilizers, with 30 to 150 becquerel per kilogram. The potassium intake with food is about 90 becquerel per day. And as I said, the total activity of potassium-40 is 4,000 becquerel per kilogram. The dose from potassium-40 to people is about 0.15 millisievert per year, and the total dose from all natural radionuclides in the body is about 0.3 millisievert per year on average. Here is a list of radionuclides from primordial radionuclides. There are a lot, and all of them have very, very long half-lives. So this is zirconium 10 to the 19 years, so it's nearly stable. So they exist really since very, very long time. However, the activities of most of these radionuclides in the Earth is very low. These are cosmogenic radionuclides. It's tritium is the most important. Beryllium-7 is continuously generated in the upper atmosphere, as well as beryllium-10, carbon-14, sodium-22, silicium, phosphorus, argon, 39, krypton 81, and krypton 85. So radioactivity is always around. So coming to the exposure from radionuclides, from natural radionuclides. The terrestrial exposure is from radionuclides in rocks, in soil, in construction material, in plants. And the activity in this material causes an external radiation, external exposure to people. And in total, on the average, is about 0.4 millisievert per year. Then we have the inhalation of radon. Radon is part of the uranium decay chain, which is from uranium-238 down to stable lead. And radon is always around. The radon gas emanates from soil and from some construction materials. The exposure varies widely, and it's about 1 to 10 millisievert per year. The cosmic radiation depends in particular on the height above sea level. This is the annual dose. This starts from 0.3 millisievert per year at sea level, going up to 3.5 millisievert per year for the Mont Blanc. This is the highest mountain in Europe, and its altitude is about 4,800 meters. So we have here the internal exposure with food. As we said, the internal exposure is 0.3 millisievert per year. And if we look at it all together, all sources together, this is a compilation of the ONSCEAR 2008. ONSCEAR means United Nations Scientific Committee for the Effect of Atomic Radiation. So we have here ingestion, inhalation, external exposure. This is a global mean, and the range. It's not the full range, but a typical range. And if you look at that, the ingestion varies from 0.2 to 1 millisievert per year. The inhalation from 0.2 to 10 millisievert per year is about, in particular, due to the inhalation of radon, and external exposure 0.6 to 2 millisievert per year. And in total, the range is about 1 to 13 millisievert per year. However, there are areas on the Earth where the annual dose from natural sources is even higher than this upper range. So this varies widely. We have also medical radiation exposure. This is mainly due to diagnostics applying X-rays and computer tomography. The doses per diagnostic examination varies widely depending on the organ or tissue which is examined. For tooth, it's quite low, it's 10 microsievert. But if you come to computer tomography, which is when a number of X-ray images are done, doses maybe up to 25 millisievert, depending on the organ and tissue which is examined. In total, the global average for the medical exposure is about 0.6 millisievert per year. However, this has an increasing trend since, in particular, the application of computer tomography is increasing. So a short summary. We have seen that the natural exposure varies widely. The global average is about 2.4 millisievert per year. And if you go for the lifetime, and we assume a lifetime about 80 years, you all know this may vary. We come up to about 200 millisievert per life. The global range, the annual dose is 1 to 13 millisievert per year. Lifetime dose is approximately 80 to 1,000 millisievert. The level of the natural exposure and its variation is an interesting quantity because it may be used as one, but no, it's not the only one, yardstick to evaluate the relevance of exposures from other sources. Such comparisons should always be taken with some care. However, it is at least one yardstick for the evaluation. Okay, thank you very much so far.